So the first thing, if I see this kind of problem on the exam in the future, I will just draw another column here. So these are the actual voltage output, and there must be a column to include all the ideal output as well. So for example, is that quiz 2, homework 2. Digital input, V out, yeah, I didn't put a VREF here in the problem, but from here you can actually tell it's 5 volts, it's 3-bit. So 5 over 3 will be 0.625. Ideally, this should be 0 volts, 0.625 volts, and the next one is 1.25, and next 1.875, and next 2.5, and 3.125, 3.75, 4.375. It's just a 0.65 increment for each step. That's what the DAC is supposed to do for the output. So if you would like to draw it, which is fine, I think, sometimes it helps. Just draw the transition diagram. Do you want to draw it? I mean, if you need to draw it, just draw it, right? But I think it just takes time. It's going to take like 50% of the class just to draw the diagram and do the analysis. But we are just looking at every single step. So for DNLs, it's comparing to the ideal step, and the ideal step is 1 LSB. So from here to here, from 0, 0, 0 to 0, 0, 1, it is correct. So you do have a 0.625 here. So there's no DNL at where? So keep in mind, it's getting confused because some of the students are, they don't know, if they see a difference here comparing to the ideal output, but they don't know what is that DNL subscription, it's footnote, it's DNL what? Is that DNL what? So DNL 0 is 0, of course, right? But for DNL 1, it's also 0. And then 0, 1, 0 is supposed to be 1.25. So here is 1.25, but it's actually at 1.5625. So actually this step is like this. And you have to find out the gap here because that's the actual step size and minus the ideal step size. So the DNL happens at where? 2. So DNL2 is, yeah, but let's do the calculation. So you want to find out that difference. You know this one, and you know the ideal. No. So you know this one, you know the original height. So this one minus this one is the step size. And over the ideal step size, and you are getting how many LSBs? How many LSBs? Because this is one LSB, and that's a step size. So this is how many LSBs, and you want to minus one LSB from here, so you can get a DNL in terms of LSBs. Right, so DNL2 is the first DNL you have, and which is 0.5 LSB. So what's the next one? So just keep going. 010 has something, and 011 it should be at 1.875, but it's actually at 2. So it's like this. Two volts. So you have a DNL here as well. So DNL, well, you have to compare these two. You're comparing the step size, right? So 2 minus 1.565 is about 0.4 something, right? It's less than 0.6. So there's a DNL. Is that DNL2 or DNL3? 3. And that equals to 2 volts minus 1.5625 over 0.625, minus 1 LSB. It's minus negative 0.3 LSB, right? And then you look at here, this minus this is 0.5 volts, it's less than 0.625. So this step size is not correct as well. And you are looking at this one, it's going to be DNL4, 2.5 minus 2 over 0.625 minus 1 LSB, which is negative 0.2 LSB. And 3.125 minus 2.5. So for this step, and it's correct, it's 0.625. So there's no DNL here. And for these two, apparently it's smaller. So it's 3 point, so this is DNL 6, 3.4375 minus 3.125 over 0.625. Negative 0.5 LSB. And this one as well, this is way larger than 1 LSB. So there's a DNL 7, 4.375 minus 3.4375 over 0.5. So we have 2, 3, 4, 6, 7 have DNLs. Because this minus this is 0.5 volts, it's not 0.625. So it's measuring step size. It's all relative. It's measuring all the gaps in between these two, comparing to 1 LSB. It's different from the NL. NL is actually easier to calculate. Pretty good on that. Yeah, a lot of confusion here. Next, NLs. So the definition for NL is it's measuring the absolute values, which will be the difference between these two, not these two. So what's the first NL? Wait, they're all the same. Here I got a difference. And that's NL what? 2. Which minus which? It's always the actual one minus the ideal one. Similar to the DNLs, it's minus the 1 LSB because 1 LSB is the ideal step size. It's always minus the ideal one. The actual one minus the ideal one. So here's the actual one. Here's the ideal one. 1.5625 minus 1.25 over 0.625. Minus 1 ISB or not? See here, we compare to 1 ISB, but here, no, it's absolute value. Absolute value. This is not comparing to 1 ISBs. It's just measuring the difference. And over 0.625, so you can get how many LSBs. So this is 0.5 LSB. And here, NL3, so it's 2 minus 1.875 over 0.625, which is negative. Wait, is that negative? No, it's 0.2 LSB. INL6, because 6 here is a difference between these two numbers. 3.4375 minus 3.75, 0.625, negative 0.4 and 0.5 LSB. INL7 is 0, so there's no NL7. So for NLs, we only have 236. Any questions on this? Hopefully this is clear. So think about that. If we have a ADC chip fabricated and we receive the chip, okay, we received it, and we're trying to test it and get all these parameters out of it to be listed as specs for this ADC performance of the ADC. And someone probably want to know the DNLs and NLs as the parameters for the ADC. How to test it. So now, like senior sun team, you guys, right? Chip is received. I get ADC, I have analog input, digital output. That's a DAC. It's a different story, but similar, right? So if you have a 1 volt B range for ADC, for example, it's 1 pin as an analog input, 8 digital output, and you have a 1 volt VREF. So you actually can calculate for every single step for all the quantization voltages for the input, right? Because 1 volt over to the eighth. So that's every single step. And then you need a curve. For ADC, it's different. For the x-axis, it's an analog voltage. It's a lot. And for here, will be the 8-bit combinations. It's going to be a lot. So how to test it? I haven't thought about it, but just right now, let's think about it at the same time, all together. How can I test every single step? So you can find out DNLs and NLs. So the input has to be an analog voltage, right? Is there any way you can automate that input to make it a LSB increment every time, and you receive an output in the digital format and measure it, so you can log it to the spreadsheet, so you can do the calculation, or in MATLAB, so you can directly plot it. How can we do that? But there will be a lot, right? 2 to the eighth. If you manually do it, it takes time, but it's fine, I think. 2 to the eighth is what? 256? So it's totally 256 combinations. And you have to have a function generator or power supply and manually set up that voltage input manually one by one. Or if you can buy a DAC, just buy a DAC chip. So it's high performance DAC chip compared to ours must be a commercial product, like 14-bit or something, right? So you can, the DAC chip, you can buy it. It's gonna send that analog voltage to here, and since the DAC has all the digital pins like D13 to D0, and you can use the microcontroller to write all the digital code, so you can automate that increment. Do you get that? Do you know how to do that? Just write a C++ code in Arduino and feed this digital signal to here, and just have a 1 LSB increment every time. So you can have that increment here as an analog form here as well. So it's feeding into here. But you buy this DAC. And for here, you can imagine there will be a digital output every time for each increment. And you can have another microcontroller here to read it in parallel and log it to a TXT file. Does that make sense? So you can directly lay out all the values into columns. All right? Some comments on this application in real life, in real world. Yeah, because we are going to have a layout, a larger scale layout starting from next week. So this week, just MOSFETs. So starting from next week, we're going to have some larger scale layouts, and you have to understand what are complex logic and AOI logic. The starting point is still from the MOSFETs. So we all know that the metal oxide semiconductor field effect transistors, right? MOSFETs. We have NMOS and PMOS. And if you want to turn on this NMOS, you have to apply a VGS voltage, because here's gate, here's source, here's drain, here's gate, here's source, here's drain for the PMOS. To turn on the NMOS, VGS, which is the voltage difference from G to S, that's why it's called VGS, has to be larger than or equal to VTH N, so that's the threshold voltage of the NMOS, that's called VTHN. That's how I can turn it on. For PMOS, VSG is from source to source to gate. VSG, the voltage difference from here to here, has to be larger than or equal to VTHP in order to turn it on to allow current flow through the channel. That's a requirement. But now I think still, before we get into the logic gates, you need to understand the NMOS is good at passing zeros but not ones. And why is that? So let's look at this NMOS. VG. So usually when we turn it on, we just short it to VDD. Because we don't have any other intermediate voltages in digital, right? It's either VDD or 0. So it's either 0, 1, 1, 0, 0, 1. So VDD will be 1, logic 1, and 0 will be ground. So we try to turn it on, so we give a VDD here, and we want to pass a 0 to here. Are we able to do that? Pretty much, I think it's fine, because you think about that. If you have, or let's say, I want to pass a 0 from here to here. So if I ground here, am I getting a 0 here as well? It's going to be very close to 0. Because VDD minus 0, you have a VGS, which is larger than VTHN, so the channel is on. It's shorting here to here. Or you can say it's pulling this pin, it's pulling this node to the ground. The ground is pretty strong ground, it's 0 volts. It's pulling it down to the ground. So you can pass 0, or you can say I'm passing 0 to here. It won't be exactly 0, but it's very close to 0. All right? So NMOS can comfortably pass a 0 volts to here. Clear? Now I'm going to start increasing this voltage. Because this is an open channel, so when I'm increasing this guy, whatever voltage here, like Vs, will be passed to here as well. Until when? Until where? Until which one is equal to where? These two? So it's passing this voltage. You can treat these two guys as the same voltage. It's not flowing current, still not flowing current yet. I'm just passing the potential from here to here. So think about that. I have this one hooked to VDD. That's the highest VG I can get, like gate voltage, VDD, the highest voltage we have in the circuit. And now I start increasing this source voltage until when there will be a point that it's going to shut off this NMOS. And what's that voltage? Before that. Because you need, or so for this equation, that's a requirement to turn it on, right? So there's a threshold voltage. It's not, and threshold voltage is not 0. It's like, for example, the 500 nanometer technology is like somewhere around 0.8 volts. So if you move this one to the left side of the equation, you're getting VGS minus VTHN larger than or equal to 0. So VGS has to be larger than VTHN, and which is a non-zero voltage. So what if when this point is VDD, when this one reaches this voltage, and you can calculate for the AVGS at this moment, VG is VDD minus VS which is VDD minus VDD plus VTHN cancelled barely equals to VTHN, right? And that's a requirement, that's a bottom line to keep it on. So any voltages higher than this one appear at the source will do what to the NMOS? Will shut it off. So any voltage higher than this voltage appear at the source pin will shut off this NMOS because of this. Because your VG, since here we're trying to turn it on, I have to apply a VDD here, the logic 1 to turn it on, right? And now I'm trying to pass all the voltage here to here. Why I want to pass the voltage to here, you'll get to that point pretty soon because we are trying to design the logic gate. So we have to pass the voltage from here to here. So we are trying to 0, fine, comfortably passing 0 to it because VDD minus 0 is still VDD. It's way higher than VTHN, higher than the threshold voltage. It's going to turn on the NMOS. But whenever you are increasing the voltage at the source pin until this point, VGS equals to VTHN, which is the bottom line to keep it on. But after that, it's going to shut off the NMOS, and the voltage potential here cannot be passed to here. So which means any voltage higher than this one cannot be passed to here. So the question is, so the conclusion here is, the NMOS is not good at passing ones. Why? Because this is less than 1. And we don't care about other voltages. We only care about 1 or zeros. It is able to pass 0, but not able to pass 1 because this is not 1. Compromise the 1. Like VDD minus VTHN, it's less than 1. What about PMOS? So the voltage difference from source to G has to be larger than VTHP in a it's a little bit higher than VTHN, but VTHP is like 0.9 volts or something. You have 5 volts. It's usually a 5 volts for your circuit in electrical VLSI, C5 technology. And for PMOS, let's try to pass. For example, I got a, here's VG, here's VS, here's VD, right? So I'm trying to pass a VDD. If I want to pass something from one side to the other side in the PMOS, I want to turn on the PMOS, right? It's a digital circuit. You only have 1 zeros. And if I want to turn on the PMOS, I should connect the VG to where? Only 2 choices. You only have 2 voltages in any digital systems, right? I want to turn on the PMOS. So should I connect VG to where? To ground or to VDD? If I want to turn it on. Wait. You have to have a VSG higher than VTHP. If I have a VDD here, VS, the highest voltage you can give to VS will be VDD. So VDD minus VDD will be 0. It's definitely less than VTHP. If you want to turn on the PMOS, you have to keep this low, right? So you can have a high VSG. Is that correct? So should short this one to ground. And now let's see. I'm trying to pass a signal. So I want to turn on the PMOS. Okay, so that's how I can turn it on. But not even guaranteed because it also depends on the VS. But at least I short it to the ground. So there's a chance, right? So now I'm trying to pass VDD from here to here. Can I do that? Is that possible? So if I turn it on, so for example, both NMOS and PMOS, they are just a switch, right? If you turn it on, it's a switch. It's going to pass the signal from here to the other side, one side to the other side. And now I'm trying to turn it on. I short the gate to the ground, and I give VS the VDD here because I want to pass VDD to here. Is that going to be passed? And why? Is VDD going to be passed to the drain or not? And why? Yes, because VDD minus VG, which is ground, is higher than VTHP. So it's higher than the threshold voltage. And it's going to turn on the channel. And so that's why it's going to conduct the potential from here to here. It's become conductive. So you're getting a VDD here as well. So the PMOS is good at passing ones, but not zeros. Why not zeros? We have seen that it's able to pass VDD to here, which is 1, no problem. So what about zeros? Why is not good at passing zeros? So let's think about it, okay? So VDD, is make the PMOS happy. You have a pretty good margin compared to the VTHP. So it's happily passing VDD to the drain, no problem. And now let's start decreasing VDD until which point it's going to stop passing that voltage to D. Until when? Here's ground, right? Here's ground. And you want to keep VSG larger than VTHP. And VG is 0. So VS, what's the smallest of VS? Could be VTHP. Because VTHP minus VG will be VTHP. Still VTHP because VG is 0. And you got a VSG will be the smallest. Because anything lower than that will shut off the PMOS and stop conducting any voltage from here to here. So the conclusion here is the PMOS is good at passing ones but not zeros. Is that making sense? That's why we got CMOS. A CMOS is not grounded. It's not from the very beginning, like the WDC microcontroller from Bill Mensch in the 1970s for the Apple II computer. This first CPU was invented. There's no PMOS. It's NMOS logic. So CMOS is a relatively newer thing. So why is it called CMOS? What is C stands for? Complementary. You got PMOS on the top and NMOS at the bottom to do the job. It's complementary. That's the first time you really understand what is CMOS. Because of this. What is this guy? An inverter, right? So whenever this pin is being pulled to VDD, which one is involved? If this one is going to VDD, you need a 0 here, right? The inverter is inverting 0 to VDD. And 0 is going to do what to PMOS and do what to NMOS? We want to keep the gate low for the PMOS to turn it on, right? And we want to keep the gate high for the NMOS to turn it on. So now it's 0 and it's being shorted to both of the gates for the two. To the PMOS, right? But this one will be off. So when you give a 0 to this inverter, what's gonna do to this circuit is actually it's become conductive here in this channel. So the VDD is actually pulling this pin up to VDD. How that works? It's just dumping a little current to this pin from the VDD, from the voltage source. All right, vice versa. You give a 1 here, you turn over the PMOS and turn on the NMOS. So the channel here is open. It's going to pull this pin down to the ground. So you get a 0. That's how you get the signal inverted. For another logic, like NAND gate. A, B as the inputs, Y as the output, 0, 0, 0, 1, 1, 0, 1, 1. Let me know what are they for the Ys. Okay, so now I'm up to design the circuit in here, and I want to implement the logic for 1s and 0s. And we know that PMOS are good at passing 1s and NMOS are good at passing 0s, so I need both. Okay, but how? So I'm looking at, since I have 2 signal inputs, so I need 2 gates, 2 transistors each time. 2 inputs, right? 1 gate, just 1 signal, cannot do anything. You need 2 transistors. So if we, because we need to turn on, you know, if you look at the 1s and 0 need to be implemented by what? Who is good at passing 0s? NMOS. So we need NMOS to do this job. And I need both A and B's to be on. So it seems like it's 2 NMOSes in series. I need to turn on both to do the job. Is that correct? Think about it. 1, 1, you got a 0. While bar on the top. Do we care about the bar? No, because Y equals to AB bar. Just treat this one as a black box. Doesn't matter, just whatever, right? Box. So 1, 1, according to the truth table, 1, 1, you have a 0, done. That's it. So this part of the truth table is done. Implemented by this NMOS. 2 NMOSes in the string. Now I need to figure out the 1s. PMOSes are good at passing 1s. And if you look at logic here, all right, I want to pull the output to VDD whenever I have at least a 0 for either A or B. Because you can see I have 2 zeros, I have 1 0, 1 0, so I always have at least a 1 0, then I'm done. So I have 2 PMOSes. You need a 0 to turn on the PMOS, and they're in parallel. So whichever or both are being turned on, you get this one put up to VDD. Is that correct? Is that correct? So I got a 1. So these ones are implemented. So this can do the job. And now, because this is AB NOT, this is also AB NOT, it's the same signal, so I can directly put them together so they can implement the full logic in the truth table. And that's how you can get the NAND structure or circuit at the CMOS level, the complementary MOSFETs. Pulling up or pulling down for all the values, all the Y's in the truth table. Any questions? No? Doesn't matter because whenever these are on, these are off. Because when you have both A and B's are ones, both of the PMOSs are off. So it's not, they're not competing. Either this one is working or these ones are working. Which won't happen is like both of these are on, is trying to compete, drag to the top or drag the output to the bottom. That won't happen if you just explore all the inputs combinations. That just won't happen because whenever you get a 0 in either A or B, you shut off this string here, right? Okay, that's explained. And next, let's look at any arbitrary logic. See if we can design a circuit out of it. Yeah, NAND gate, NOR gates, we can implement this logic in CMOSes, but definitely for other logic as well. For example, a very similar one. Y equals to A, B, C not. How can I design a circuit out of it to implement this logic? You are thinking, hey, it's a 3-input NAND gate. Boom, boom, boom. A, B, C. But what's inside? That's the question, right? Can you do this? Huh? Is that correct? So what's the signal here? So what's the signal here should be? It's different. What about this? That's fine. But this is not correct. But now we are not even talking about this. If you do this, which means you have, yeah, let's think about this one. If a NAND gate, definitely you can do this. You'll say, hey, this is NAND, right? It's the inverter. So that's the AND. Is that correct? The AND gate? Because NAND gate is being inverted, right? As a 2-input AND gate. So you think, hey, if I need a 3-input AND logic, I just drew another of this. Just copy it. Just duplicate it, do another one, and short this one to here, and get a C. So I got ABC. You want to do that, and then invert it. So get this. Doable, but just not ideal. It's taking a lot of space. So 3-input NAND gate is simply just this. That's it. Compared to this one, it's a lot easier, taking a lot less space. So this is just one example. It's called AOI logic. And or inverter inverting, invert probably. So if you use and or invert, you can implement any logic in the CMOS version. That's what we are going to do because it's saving a lot of space. I want to do it. All right. But how? Look at these versions. Look at these circuits. So first, it has to be something bar as a structure of it. So there's a lot of memorization. You want to remember it. After you verify it's correct, just memorize it. That's a way you want to follow. So you can design any CMOS circuits from any logic. It has to have something at the bottom, it has to have a bar on top. And if you have this logic expression, you want to convert into a CMOS or AOI logic, like this. It has to be, when you have and logic, you have to have parallel PMOSes on the top and series NMOSes at the bottom. If you have an OR logic, you should have series PMOS on the top and parallel NMOS at the bottom. And that's it. That's how I can remember it. And if you do not have something bar, then convert it to something bar. De Morgan's law, remember? Converting, eventually you get a something bar. And then follow the rules. Let's find an example here. Have example. Yeah, for example, this one. Y equals to A not or BC. There's no bar. So make up a bar. Bar. Right? You got two bars this time. So apply De Morgan's law to the bottom version, to the bottom part here. De Morgan's law, split the bar, change the sign. Split the bar, change the sign. Right? And don't forget the top bar here. And this one equals to A, bar is still A. B, split the bar, change the sign. Right? Now you have something bar. So you're ready to convert into AOI logic. So you want to look at this one first because this is the final operator after this one, right? If you're doing calculation, you want to consider this one last, right? So A and something. So if this is a black box, A and something is AND logic. So you need, just always think about the non-circuit. Non-circuit, you have parallel PMOS on the top. So parallel PMOSes. And parallel, it's a black box here for this guy. And it's OR logic, so you need a series PMOSes on the top. For these two. You say, I need an inverter here. So it's just directly, I just directly use the signal. I just treat this one as a black box. This is the B bar signal. And that's for the top. For the bottom, for AND logic, it has to be something series with something, which is this guy. And the OR logic, it has to be in parallel. NMOS, sorry. and grounded. So B bar, C bar, and here is A. Here's A, B bar, C bar. And this will be A and B bar or C bar not. That's how to design the CMOS circuit. If you draw them in logic gates, which is fine, but it's going to take a lot of space. And see, look at this one. Only it's a 6 transistor circuit. Done. Any questions? Okay, we'll give you guys more examples next time. All right. We forgot to do the quiz. No, Wednesday. All right. Wednesday we'll do the quiz.